In this session, we will be seeing types of molecular velocities. Molecular velocities we are considering here as root mean square velocity, average velocity and most probable velocity. So, these three velocities, their equations and also some of the problems based on this will be discussed in this session. Now, let us move on to the topic. Now, the types of molecular velocities discussed here are average velocity, root mean square velocity and most probable velocity. Now, we all know the fact that velocities of gas molecules depend upon molecular mass and temperature, that I have already mentioned in the previous session. Like if molecular mass increases, the velocity tends to decrease. When temperature increases, velocity increases. So, just keep that in mind. Now, three types of molecular velocities are derived from Maxwell-Boltzmann distribution equation. Maxwell-Boltzmann distribution of molecular velocity distributions. So, let us see one by one. First one is the average velocity, which is represented by small v. Average velocity of a gas at a given temperature is defined as the mean of velocities possessed by all the molecules at that temperature. Just take the average. Take the velocities divided by their number of molecules. Okay. Now, consider n molecules of a gas and let the individual velocities of the molecules 1 to n be C1, C2, C3 and so on up to Cn. Now, the average velocity V can be represented as C1 plus C2 plus C3 plus so on up to Cn whole divided by capital N. Okay. This is when we are having a same type of molecules in that gas. If we are having a group of different molecules where we are going to consider that N1 molecules will be having a velocity C1. Another set of molecules, let the number be N2, they possess a velocity C2. Another set, we are having N3 molecules having velocity C3. Now, if this is the case, the average velocity will be equal to, that is N1 molecules with velocity C1 plus N2 molecules with the velocity C2 plus N3 molecules with the velocity C3 plus so on whole divided by N1 plus N2 plus N3 and so on. But since the total number of molecules is capital N, then that will be equal to N1 plus N2 plus N3 plus so on. Then V is equal to N1 C1 plus N2 C2 plus N3 C3 plus so on whole divided by capital N. So, this is the average velocity. Now, solving Boltzmann's distribution law equation of molecular velocities, it has been found that the average velocity V is equal to square root of 8 RT by pi m. You have to by heart it. V is equal to square root of 8 RT by pi m. So, there is equation because we need this for solving problems and all. Next is the root mean square velocities. It is, we have already mentioned it, it is a square root. First, you have to take the square root of what? Of the mean of squares of velocities. That is, you have to take the squares of velocities. Then, what I have to do? I have to take the mean and then take the square root of it at a particular temperature is defined as root mean square velocity or RMS velocity. So, if you are having number of molecules, different molecules with the velocity C1, C2, etc., and the total number of molecules is capital N. Here the C1 square plus C2 square plus C3 square. Now, this becomes the squares of the velocities, so on. You have to take the mean, so I will be dividing it with capital N, okay, and you have to take the square root of this. See, we have taken the mean of squares of velocity, okay, and then its square root. This becomes RMS velocity, which is denoted by the letter small letter u. Okay, consider n molecules of a gas, okay, where the individual velocities for 1 to n are C1, C2, C3 up to Cn, and we are going to assume that there are n1 molecules having a velocity C1, n2 molecules having a velocity C2, n3 molecules of velocity C3, and so on. Then we can write this in two forms. This is for total number of molecules. We have given 1. The next is u equals square root of what we have done in the previous case, n1 C1 square, n2 C2 square plus n3 C3 square plus so on, whole divided by n1 plus n2 plus n3 and so on. And this value, as we have seen, that will be equal to capital N. So, that will be equal to square root of n1 C1 square plus n2 C2 square plus n3 C3 square plus so on, whole divided by capital N. Okay, this is root mean square velocities. Now, on solving Maxwell-Boltzmann distribution law equation, it has been found that the root mean square velocity u is equal to square root of 3 RT by m. The other case, it was 8 RT by pi m. Remember, v is equal to 8 RT by pi m. In this case, it is 3 RT by m. This is RMS velocity or root mean square velocity. Next type of velocity is the most probable velocity. If you recall, in the Maxwell-Boltzmann distribution plots, here we have the probability, and here we have the velocities, and you have a graph. Okay. The most probable velocity is the velocity possessed by maximum number of molecules, and this was considered as the most probable velocity alpha. The most probable velocity of a gas at a given temperature is defined as the velocity possessed by maximum number of molecules at that temperature. Maximum number of molecules possessing that velocity is known as the most probable velocity, denoted by the letter alpha. And solving Maxwell-Boltzmann's equation, you can get an expression for that, that is most probable velocity alpha is equal to square root of 2 RT by m. Square root of 2 RT by m. Root mean square, it is 3 RT by m. And the average velocity, it is 8 RT by pi m. Okay. Now, let us see what is the relation between these molecular velocities. V equals 8 RT by pi m. What is V? That is the average velocity. Now, U is the root mean square velocity. I am going to take V in terms of U. So, what I am to do is, I want, that is U is equal to square root of 3 RT by m. This is what U is. So, I have to convert this fraction in terms of 3 RT by m. So, what I am going to do is, the square root of 8 RT by pi m, I am multiplying this both numerator and denominator with 3. Both numerator and denominator with 3. See, this is a 3 over here and this is another 3. So, I am taking the 3 here and the 8 outside. So, it becomes 8 by 3, 3 RT by pi m. Now, I have got a chance to convert this. I can take 3 RT by m as this is the factor root mean square velocity u. So, 8 by 3 pi is taken out and the rest is represented as u, and if you calculate that, you will get it as 0.921 u. Next is the most probable velocity, that is equal to square root of 2 RT by m. Again, to convert that in terms of root mean square velocity, I am going to multiply both numerator and denominator with 3. We will get this as 2 by 3 into, or should I represent it again? Just 2 RT by m. I am multiplying that both numerator and denominator with 3. So, I will take the 3 to this side and 2 this side. So, it becomes 2 by 3 to 3 RT by m, and that is equal to the 3 RT by m, you can write it as u. So, square root of 2 by 3 u, solving I get it as 0.816 u. So, again this is expressed in terms of u. Now, we have the two expressions, v is equal to 0.921 u and alpha is equal to 0.816 u. So, when I take the ratio, if root mean square velocity is taken as 1, the other two will be, that is most probable 0.816, the other one is 0.921, that is the average velocity. So, root mean square has got the highest value. Next comes the average velocity and most probable velocity is the lowest one. Next, we are going to see the relationship between RMS velocity and density. RMS velocity u is equal to square root of 3 RT by m. Now, here we do not have any density term. Now, what we are going to do is, we know that from ideal gas equation PV is equal to RT. Now, I am going to substitute for RT as PV here from ideal gas equation. RT is substituted as PV. Now, it becomes square root of 3 PV by m, and we know that what is density? Mass by volume. Density mass by volume. Now, we have both mass and volume. The only difference is, here we are having volume in the numerator and mass in the denominator. So, what I am going to do is, I am going to bring this downward. So, it becomes divided by V. So, 3 P divided by m by V. So, this term represents the density denoted by the letter D. Okay. So, substituting, this becomes u is equal to square root of 3p by d. Now, just see that as the density increases, the most probable root mean square velocity or whatever be, this is a root mean square velocity. When density increases, that is when density increases, that is naturally when mass increases. What is happening to that? It is in the denominator. What will happen to the velocity now? It decreases because that is in the denominator. So, the effect of density is as density increases, u decreases. That is the root mean square velocity. Now, let us go for some problems based on all these velocities, that is RMS velocity, average velocity and most probable velocity. Here the problem is calculate the RMS velocity, average velocity and most probable velocity for nitrogen molecules at a temperature 273 Kelvin. The temperature is given in Kelvin and the atomic mass of nitrogen is equal to 14. Okay. We will write the data. Temperature is equal to 273 Kelvin. Mass, molecular mass of nitrogen, they have given atomic mass of nitrogen as 14 and we all know that the molecule of nitrogen is represented as N2, that is 2 atoms together, okay, diatomic, and therefore 14 into 2 into 10 to the power minus 3 kilogram per mole, that is the molecular mass of nitrogen gas. R is equal to 8.314 joules per Kelvin per mole, that is its unit in SI system. Now, we have the expression for RMS velocity, u is equal to square root of 3 RT by m. We have all the values here. So, I can put it as square root of 3 into 8.314, temperature is 273, whole divided by the molecular mass 14 into 2 into 10 to the power minus 3. This is Kelvin. 3 R is joules per Kelvin per mole. Okay, and this will be molecular mass kilogram per mole. Okay, the per mole and per mole gets cancelled. Then Kelvin and Kelvin gets cancelled. You will get joules, and joules you can make it as kilograms per meter square per second. Kilogram meter square per second square. Okay, so that is there. Now we have here joules have been converted. So the kilogram and kilogram gets cancelled. Okay, and we have the square root. So it becomes meters per second. Got it? This is the unit. And when we solve this, the answer is 493.14 meters per second. Just imagine what's the speed. So many meters. They are traveling such a huge distance per second, that is of nitrogen molecule. This is the RMS velocity. Now, we want the average velocity. Average velocity V is equal to square root of 8 RT by pi m. All these values we have already written there. So, I can just write it here itself. The value 8 into R 8.314, temperature was 273. Whole divided by the value of pi is 3.14. and molecular mass is 14 into 2 into 10 to the power minus 3. I am not writing the units here, it will be in meters per second because it is the same thing. Okay. On solving, we will get it as 454.45 meters per second. This is the average velocity. You just see that RMS velocity is 493.14. This is reduced to 454.45. Now comes the most probable velocity alpha, which is equal to RT by M, 2 into 8.314 into the temperature was 273 whole divided by the molecular masses 14 into 2 into 10 to the power minus 3, and solving you will get it as 402.65 meters per second. Since all for one I have shown the units how we will get it, you can do it by yourself. Now, the numerical values I have given, that is 402, and here also you can check the least value was obtained for most probable velocity, then average velocity, and the highest value was obtained for root mean square velocity. Okay. Let us move on to the next problem. Calculate the temperature at which the RMS velocity of nitrogen equals that of carbon dioxide at 300 Kelvin. So, carbon dioxide will be having a particular root mean square velocity at 300 Kelvin, which we can calculate, and you will have to find out the velocity which nitrogen will be having, same velocity what the carbon dioxide has at 300 Kelvin, and the temperature at which the nitrogen shows that velocity has to be calculated, because you can see that the molecular masses are different for nitrogen and carbon dioxide. Naturally, the temperature for nitrogen will be different, though the RMS velocities of nitrogen and carbon dioxide are equal. Now, let us see the data. Temperature of carbon dioxide is equal to 300 Kelvin. Molecular mass of carbon dioxide is equal to 44, which is obtained from carbon 12, oxygen atomic mass is 16, and you have carbon dioxide means CO2, that is mass of carbon plus 16 into 2, that is oxygen, because you have 2 oxygen molecules, and that will be equal to 44 into 10 to the power minus 3 to convert it into kilograms. R is equal to 8.314 joules per Kelvin per mole, and molecular mass of nitrogen is equal to, remember it is a diatomic molecule, so atomic mass multiplied by 2 into 10 to the power minus 3 kilogram per mole. So, these are the data, and we know that RMS velocity, the equation is square root of 3 RT by M. This is the RMS velocity, and we are supposed to find out the temperature. So, it is better we equate, because the RMS velocity of carbon dioxide and nitrogen are equal, we can equate the equations because their RMS velocities are equal. Okay. So, what I am going to do is, I am going to write the RMS velocity U for nitrogen, that will be equal to square root of 3 R temperature of nitrogen divided by molecular mass of nitrogen. That is, in the case for RMS velocity of nitrogen, when I am taking the RMS velocity of carbon dioxide, the equation will be square root of 3 R T of carbon dioxide divided by molecular mass of carbon dioxide. Okay. Now, since these two are equal, I can equate both the expressions. That is, since I have to find out that of nitrogen, I will write first nitrogen square root of 3 R T of nitrogen divided by molecular mass of nitrogen to be equated to square root of 3 RT of carbon dioxide whole divided by molecular mass of carbon dioxide. Now, since both the sides we have root, you can square both or you can remove the root. I can write this expression as 3 RT of nitrogen divided by molecular mass of nitrogen will be equal to 3 RT of carbon dioxide divided by molecular mass of carbon dioxide. Okay. Now, I am going to cancel the similar terms, 3 get cancelled, R get cancelled, and finally, the expression is T of nitrogen divided by M of nitrogen is equal to T of carbon dioxide divided by M of carbon dioxide. The equation has been simplified and we are supposed to find out the T of nitrogen. So, I will keep the expression as T of nitrogen is equal to T of carbon dioxide divided by M of carbon dioxide, and I am going to take this molecular mass to this side. So, this becomes multiplied by molecular mass of nitrogen. Now, I am going to substitute the values T of carbon dioxide 300 Kelvin. Molecular mass of nitrogen, that is 14 into 2 into 10 to the power minus 3. So many kilograms per mole. This is Kelvin. Temperature divided by molecular mass, 44 into 10 to the power minus 3 kilogram per mole. Okay, kilogram per mole cancels here, both get cancelled, and finally, when you solve for the answer, the unit will be in Kelvin. So, by solving, we will get it as 190.91 Kelvin. See, here in this case it was 300, and in the case of nitrogen it has got the same velocity at a lower temperature. Can you guess why is it? Because nitrogen, its molecular mass is lower, while that of carbon dioxide it is higher. Okay. Now, I will give you an assignment which I will be discussing in my next session, that is calculate the RMS velocity of oxygen molecule at 25 degree Celsius. Very easy question. Just find out the RMS velocity of oxygen molecules at 25 degree Celsius. Now, to conclude, in this session we have been seeing types of molecular velocities, that is average velocity V, given by the expression V is equal to square root of 8 RT by pi m. Then root mean square velocity or RMS velocity, U is equal to square root of 3 RT by m, and most probable velocity alpha is equal to 2 RT by m. And that is all for this session. Have a nice day. Thank you.